Thank you. Okay, so yeah, we missed some slides over here. So there's a thank you note which was missed. And this is where we start now. Okay, so hello everyone, and welcome to Google. I'm Phaneendhar Vemuru. I'm a tech lead on Cloud Bigtable. And today we wanted to talk about some of the lessons we've learned when we started running Bigtable in a production setup at Google. So there's also going to be another talk which is going to concentrate a little more on Cloud Bigtable. Max sitting over here is going to talk about it a little more. But I'm going to concentrate a little more on like the core Bigtable technology and some of the lessons we learned when we just started using it in Bigtable within Google. So before we get started on this, it's important to realize how the growth of Bigtable within Google was. For lack of a better word, it's phenomenal, spectacular, and totally unexpected. Nobody in Google, I guess, even dreamed that it will grow at the rate at which it grew, right? So it grew to an extent that like hundreds of projects and hundreds of products outside Google, which are visible to users, started using Bigtable much sooner than we expected. And some of these users were pretty large too. And I mean, everyone knows that it was built for a certain use case, which was large enough. But like a lot of users were actually storing petabytes of data and performing millions of operations a second. And the growth was phenomenal. So as a consequence of this, the phenomenal growth, we quickly realized that we were managing a lot more data than we expected. And also that we are also managing a whole wide different range of clients than whom we expected, right? We expected batch workloads, we expected search index kind of things, but we also started seeing people who are actually storing user data and serving user data out to the out as a product requirement. So it surprised all of us. So the thing that we noticed immediately was with the scale that comes, like if you start storing enough data in a table in a system like Bigtable, eventually corruptions will creep up. And one might ask, like, why is it that corruptions are a thing for this storage system, or like HBase or Bigtable? Why are corruptions so important for Bigtable, and why don't we talk about them that much in other storage systems? Well, for one, as our community talks about, we talk about write amplification, right? So this is one aspect of write amplification which comes up, right? Like all the data that is written into HBase or Bigtable, depending on your major compaction cycle, is completely rewritten. So you have, like, if you imagine, like we weren't prepared for the amount of data that will be stored in Bigtable. All that data, pretty much that whole amount of data, is rewritten every, let's say, 1 week, if the major compaction cycle was 7 days, right? So what that essentially means is like you're moving this streams of data across hardware and software, and those streams might get corrupted at some point, and the frequency gets pretty bad if the amount of data you're storing is pretty large. I mean, if you're not storing lots of data, it'll happen at some point in the future. But for us, it got to a point where if we didn't do something special about it, we would have actually hit corruptions pretty much daily on our SS table writing compactions, right? So I just put in like 3 different categories over there. We had metadata corruptions, which happened yearly, but I mean, pretty much all of us understand that metadata corruptions are going to be a lot more disastrous, and we can talk about that in a minute. But even if they happen yearly, they can take down a whole cell or a whole cluster in that year. And SS tables, we wrote so many SS tables in a day that there used to be at least one corruption. And it's a good thing that we actually handled them. Otherwise, we'd have had like problems every day, literally every day, having some data not being servable. So I'm going to concentrate a little bit on corruptions and what we did internally for Bigtable to deal with these corruptions, and the features we built to make some of this management of this thing. Some of they will happen at some point, even if you do all the things you can. And once they happen, what kind of things can you do to make it easier to manage? So no surprises there. It takes a lot of discipline to actually build end-to-end checksumming, but end-to-end checksumming was the biggest bang for the buck, which helped us immensely. It takes, I mean, again, it's really it takes a lot of discipline, especially when there's a lot of stacks involved. There's like we had to push the checksumming from the Bigtable client to our RPC layer, to Bigtable, through the file system layer, and then to the disk, right? So end-to-end checksumming catches like pretty much most of our corruptions. And this is basically something that we want to say that, hey, this is really important, especially when you're growing in scale. But there are also other features which one wouldn't expect, which are very important in actually running a service successfully and in a way that it doesn't overburden you. And I've listed, for the different types of corruption, I've listed some of the safeguards that we have implemented. For metadata, we actually have duplicate metadata stacks. So you write metadata for a table, for a tablet. We also have duplicate pieces of metadata written in a certain way so that it helps in recovery in certain cases, and we'll talk about that. We have what is called quarantining and auto-quarantining, which basically detects problems in the system and says, okay, there's something going bad. If I don't react right now, it's going to get worse, so I'm going to intervene and do something about it. We'll talk about that. We'll talk about verification reads and what we do for commit logs and how do we deal with commit log corruptions. So, well, this should be a familiar picture for all of us, right? HBase, Bigtable, it doesn't matter. So slight terminology changes happen, but it's one and the same thing. There are a lot of user tables. User tables have user tablets. So I guess user tables have user regions in HTable terminology. And the metadata for the user tablets are stored in the metadata tablets. The metadata tablets metadata, so we're talking about metadata of metadata now, are stored in the metadata root tablet. And I guess it's kind of obvious that like if you lose your metadata root tablet, you can lose pretty much the whole cluster. And if you lose your metadata tablet, then you lose a lot of your user tables. And if you use the user tables or something gets corrupted in them, then okay, you just affect that one particular tablet, but it's not the end of the world. So, well, we all know this, but I think it's important to realize that we should be willing to, and we should be making different cost to risk trade-offs on this, and making sure that we do a little bit different in whatever we do for writing metadata tables and metadata. For instance, for metadata, we write what is called as a copy row. So we write a metadata. So every time a split happens, every time a merge happens, every time a load, unload, anything, compaction, when we need to update the metadata, our metadata updates are slow. The reason for that is they write to the metadata, but they also write to a metadata copy row. And the copy row and the metadata row both contain checksums. And the same applies on the read path. When you need to move a tablet to another tablet server, or when the tablet server dies and we need to load it, we read both the metadata copy and the metadata at the same time in parallel. And make sure, and try to use the row which seems to be saying that there's no corruption. So if one of them comes up with the wrong checksum, we auto-fix the other row, and then say, okay, I found the corruption, I auto-fixed it, and I'm going to go on with my business. And sometimes when there's no way to realize which is the row that you can use, it's a manual trigger, and then we don't stop the whole process, but we stop that particular tablet from loading at least. Right? So in addition to that, I guess from the previous picture, which I was trying to show, where there's this red metadata root tablet and saying, please don't try to lose this. This is really important. We take that. We actually make decisions based on that, right? So we make sure that our file system writes a lot more copies, a lot more replication in the file system for the blocks written for metadata tablets and root metadata tablets. So we made a conscious decision that not only is it important to do checksumming, but we will make sure that there's copies both in Bigtable level in the copy row, and also more copies in the file system level in terms of multiple replication, so that the availability of the metadata is a lot higher than the rest of the table. And yes, that means that you'll use more storage because there's much more replication file system and also copy rows, but it actually pays off. And the automatic fixing is awesome. Like when we get stats saying that there was a corruption, but it was automatically fixed because I found a copy row which was usable, that's awesome, right? No maintenance. So corruptions in SS tables. So I think we kind of understand this, right? We just talked about the right amplification, the fact that we need to rewrite all the tables, as tables are constantly being rewritten. But there's also another aspect of this. Okay, we'll talk about how to deal with SS table corruption in general, but But the immediate effect for the service to be stable is the minute you try to read data from a corrupted SS table, you detect that the SS table is actually corrupted. And it's not really clear for the code that, OK, what should I do now? I've read something from my memory, and I've seemed to have found data which seems to be corrupted. I'm not sure what happened here. Maybe the memory got corrupted, the machine is bad. So more times than not, unless you can really pinpoint a particular tablet, you just crash. Like you just say, I'm dealing with a memory, or I'm dealing with memory which seems to be wrong. I don't want to serve the wrong data to the user. I'm just going to die. But this doesn't help anyone, right? The tablet server dies. Well, the region server goes down. It gets loaded into another region server. It loads, and the client does a similar operation. We try to read the same data. The same detection happens, so there's a corruption. That tablet server dies, and it goes on. Right? It keeps going to different tablet servers and keeps killing them. So we affectionately call this tablets of death, and unsurprisingly. And we built in a system to automatically detect such tablets and auto-quarantine them. Well, so a lot of our work we do is to make sure that the system can react to certain problems that we can automate rather than have somebody come and fix it. And this helps us actually maintain the scale of operations that we'd maintain inside Google. So in this particular instance, the master keeps track of all the tablets that were getting reassigned to different tablet servers. And it realizes that, OK, in the last 10 minutes, this tablet seems to have been moved because of tablet server deaths a lot more than the other tablets. There's something fishy going on with this tablet, and it'll automatically quarantine it. What it means is that it'll stop assigning the tablet to any tablet server, and it'll not be loaded until somebody comes and manually fixes it. Manual fixing usually means the person has to look at the data, see what the corruption could be. Sometimes it's easily detectable. You can find a single bit flip and fix it. Other times you lose the data, unfortunately. But at least you don't affect the whole cluster. You fix the problem automatically, or at least resolve it. So SS tables. We found no other way to do this, but this is the best we could come up with. If there are better ideas, we'll like to hear. Essentially, after every compaction, since the compaction essentially means you're reading the whole disk, you're passing it through memory, you're passing it to RAM. Sorry, you're passing it to RAM, you're passing it to CPU, to network, and then writing back another file. We are making no assumptions that the next file is going to be good, just because the previous files are good, obviously. So we write streaming checksums while the file is being written. And once the file is written, we don't say the compaction is done. We just be like, OK, I'm still doing my compaction. And then we go back and read the entire file while performing the streaming checksums to make sure that the file is actually good. And only when all the streaming checksums work out, that's when we say, OK, now I'm going to install this new file and say the compaction is done. This is the one which I showed in the first slide, saying that if this wasn't done, we would be writing a bad SS table every day. And that means that we would be losing at least a tablet every day if you didn't have this extra protection for compactions. So we call them verification reads. And they've been really awesome for us. They worked out pretty well. So commit logs. So commit logs do get corrupted at the same rate as SS tables. But they're less of a concern because more often than not, you don't use your commit logs. Commit logs are there just in case if a tablet server dies or if a region server dies. So most times they're fine, even though if we actually read back our commit logs, we see the same level of corruption happening for the same amount of data as SS tables. These are not that worrisome, but we still have auto-quarantining built when the tablets are loaded. So when the tablets are loaded, we realize that the commit log or the write-ahead log, WL, if the log has a corruption, we try to pinpoint the corruption when possible. If we're not able to pinpoint which table it belongs to, then pretty much all the tablets that were dropped when the region server went down are auto-quarantined. If you're able to pinpoint exactly, like, OK, this is this particular tablet and there's some corruption in the data, then only that particular tablet is quarantined. Again, automatic reaction to system events is like a theme that I wanted to like say that this is the kind of things that we keep working on so that we can scale. Else we'll be having like a lot more people taking care of Bigtable within Google if we didn't automate and self-heal some things which we can. I'll only briefly touch upon isolation as to like some of the themes, and I specifically picked a couple of examples. I mean, this is a theme. This is basically not talking about all the isolation things that we are thinking or we have built within Bigtable, but talks about some of the two primary themes. And I guess it'll be interesting to discuss how these things compare with external implementation. So first thing is memory mapped SS tables. I don't know if there's an equivalent in HBase, but memory mapped SS tables essentially says that the user wants the blocks of the SS table to be served from the memory, because this particular column family, they expect to be served with much lower latency than other column families, so they don't want any cache hits or cache misses. They want always cache hits. They don't want to have a chance in that. So which is fine, but the user says like, okay, I think I'm going to expect like 1 terabyte of like, block cache to be required. That's great, but it's not like they have a good mechanism to limit it, and it's not like it happens in a single Tableau server. So the theme for most of these isolation stories where there's a resource which needs to be managed is essentially Tableau servers collecting statistics per user, per table, depending on the statistic, pushing them to the master aggregating them and sending back both the aggregated statistics and also the quota which the user claimed they will use. And the Tableau server making a decision at that point, saying that, okay, you're above quota, I'll stop memory mapping your files, right? So no more. Yes, you'll get more latency, but at least we're not going to like chew up and eat up all our memory everywhere in the system, right? So a general theme of like being able to aggregate information from across Tableau servers, master being the place which aggregates it and sends it back, and Tableau servers the decision makers of what to do with it. And the other theme is basically local. So the last thing we talked about was how we got aggregated data, but we also make local decisions within the Tableau server. So within the Tableau server, we make sure that there's at least some amount of memory and some amount of CPU available for different users and different tables, just in case. So even if you are using everything within your quota globally, like you're not using too much memory when you count the global statistics which the master is pumping back to the Tableau server. Even if you're doing well globally, for locally, just to make sure that we have some amount of bandwidth to serve other users and other tables, we cap the amount of usage you can use at any single Tableau server. So once this limit hits, you start flushing more often. So minor compactions of flushing more often, and aggressively like keep some amount of memory free, even though globally you can use more memory. So this just touches upon the couple of themes we have on like how do you deal with like global quotas and what do you do locally per Tableau server. Okay, then that concludes the talk. Thanks for listening, and I'll be around here if somebody wants to catch up and discuss some more ideas or themes around this. Thank you.